Imagine a future where humans deliberately dim the sun. Not metaphorically, physically. Tiny particles released into the upper atmosphere reflecting sunlight back into space. Global temperatures dropping within years. Ice sheets stabilizing. Heat waves weakening. It sounds like science fiction, but research into climate engineering, also called geoengineering, is already underway. As global temperatures continue rising and emissions reduction efforts struggle to keep pace, scientists and governments are asking a controversial question. If we cannot reduce warming fast enough, can we directly intervene in Earth's climate system? Climate engineering refers to deliberate, large-scale manipulation of Earth's energy balance. It is not about stopping emissions at the source. It is about altering radiative, forcing the difference between incoming solar radiation and outgoing infrared heat to cool the planet artificially. To understand this, we need to talk about radiative forcing. Earth's climate is governed by energy balance. Sunlight enters the atmosphere. Some is reflected by clouds and ice. The rest is absorbed by land and oceans, warming the planet. The Earth then emits infrared radiation back into space. Greenhouse gases like carbon dioxide absorb some of that outgoing heat and re-emit it, trapping warmth. When greenhouse gas concentrations increase, more heat is retained. This creates positive radiative forcing, driving global warming. Geoengineering strategies attempt to create negative radiative forcing. In simple terms, they try to reduce incoming solar energy or increase outgoing heat to space. One of the most discussed approaches is solar radiation management. This involves increasing Earth's reflectivity, also known as albedo. A leading concept is stratospheric aerosol injection. The idea is inspired by volcanic eruptions. When Mount Pinatubo erupted in 1991, it released millions of tons of sulfur dioxide into the stratosphere. These particles formed sulfate aerosols that reflected sunlight, temporarily cooling global temperatures by about half a degree Celsius. Scientists propose replicating this effect intentionally. Aircraft or high-altitude balloons would release sulfur-based particles into the stratosphere. These particles scatter incoming solar radiation, reducing the amount that reaches the surface. The physics behind this relies on aerosol particle scattering. When particles are similar in size to the wavelength of visible light, they scatter sunlight efficiently through a process described by my scattering theory. Properly distributed, these particles could lower global temperatures within a few years. But the system is complex. Aerosols do not simply float harmlessly. They can alter precipitation patterns. They may weaken monsoons. They can deplete ozone if chemical reactions occur on particle surfaces. Cooling the planet unevenly could create regional climate disruptions. Climate systems are nonlinear, meaning small changes can produce unpredictable feedback loops. Climate feedback loops are self-reinforcing processes. For example, melting Arctic ice reduces surface reflectivity. Dark ocean water absorbs more heat, accelerating warming. That is a positive feedback loop. Geoengineering aims to counteract these loops, but introducing artificial cooling could trigger others. For example, reduced sunlight might alter plant growth, affecting carbon cycles. Another proposed strategy involves marine cloud brightening. Ships would spray fine seawater droplets into low-altitude marine clouds. These droplets increase cloud reflectivity. Brighter clouds reflect more sunlight back into space. This method focuses on localized cooling, potentially protecting coral reefs or polar regions. But again, cloud systems are highly dynamic. Small alterations in droplet size distribution can change cloud lifetime and rainfall patterns. Beyond solar reflection methods, there is carbon dioxide removal. Instead of reflecting sunlight, this approach removes greenhouse gases from the atmosphere directly. One method is direct air capture. Large industrial systems use chemical sorbents to bind carbon dioxide molecules. The captured carbon is then compressed and stored underground in geological formations. This process relies on carbon sequestration chemistry. Carbon dioxide reacts with alkaline substances to form stable carbonate minerals. In theory, this locks carbon away for thousands of years. There is also enhanced weathering. Certain silicate rocks naturally react with carbon dioxide over long timescales, forming carbonates. By crushing these rocks into fine particles and spreading them over land or ocean surfaces, the reaction rate accelerates. This speeds up natural carbon removal processes. However, mining and distributing billions of tons of rock requires enormous energy and infrastructure. Ocean fertilization is another debated method. Iron is often a limiting nutrient in parts of the ocean. Adding small amounts of iron can stimulate phytoplankton growth. These microscopic organisms absorb carbon dioxide during photosynthesis. When they die, some sink to the deep ocean, potentially sequestering carbon. But marine ecosystems are delicate. Altering nutrient balance could disrupt food webs or create harmful algal blooms. The ethical controversy surrounding climate engineering is intense. One concern is moral hazard. If governments believe geoengineering can cool the planet quickly, they may reduce efforts to cut emissions. This could lock humanity into long-term dependence on artificial climate control. If aerosol injections begin and then suddenly stop, temperatures could spike rapidly. This is known as termination shock, because greenhouse gas levels would remain high. Removing reflective aerosols would cause abrupt warming. There are also geopolitical risks. Climate systems do not respect national borders. If one country deploys solar radiation management and another experiences drought, tensions could escalate. Who decides the global thermostat setting? Who controls deployment? Who compensates for unintended harm? Climate models attempt to simulate these scenarios. Advanced Earth system models integrate atmospheric chemistry, ocean circulation, cloud microphysics, and biosphere interactions. These feedback loop models help researchers estimate temperature responses, precipitation shifts, and extreme weather changes under geoengineering scenarios. But models have uncertainty. The climate system is chaotic and deeply interconnected. One often overlooked factor is ocean acidification. Solar radiation management may cool temperatures, but it does not reduce carbon dioxide levels. CO2 dissolves into seawater, forming carbonic acid and lowering pH. This threatens coral reefs and shell-forming organisms. Reflecting sunlight does not solve this chemical imbalance. Only carbon removal addresses that. The debate is not about whether climate engineering works in theory. Many models show that aerosol injection could lower temperatures. The debate is about risk management. Once deployed at scale, stopping becomes dangerous. Maintaining a stable artificial aerosol layer would require continuous global coordination for decades or centuries. There are also technological challenges. Delivering millions of tons of particles to the stratosphere annually requires specialized aircraft fleets. Particle size distribution must be carefully controlled. Too large, and they fall quickly. Too small, and they behave differently in scattering sunlight. Chemical composition affects atmospheric reactions. Precision matters. Despite these risks, research funding is increasing. Governments recognize that climate thresholds such as irreversible ice sheet collapse may be approaching. Some argue that geoengineering should be a last resort emergency tool, not a primary solution. Understanding its mechanics now may provide options. If warming accelerates beyond expectations, public opinion remains divided. Some see climate engineering as reckless planetary experimentation. Others view it as pragmatic risk reduction in a world already altered by industrial emissions. After all, humans have already modified the climate unintentionally. Geoengineering would be intentional modification. The deeper philosophical question is whether humanity is ready to manage planetary-scale systems deliberately. Climate engineering shifts responsibility from mitigation to control. It transforms Earth from a self-regulating biosphere into something resembling a managed environment. The science is complex but not mystical. Radiative forcing can be quantified. Aerosol scattering follows physical laws. Carbon sequestration follows chemical reactions. Feedback loops can be modeled mathematically. The uncertainty lies not in basic physics but in emergent complexity. Climate engineering represents both technological ambition and existential risk. It could buy time for decarbonization. It could prevent catastrophic tipping points, or it could create new instabilities in a fragile system. What is clear is that the conversation is accelerating. As heat waves intensify, glaciers retreat, and extreme weather events multiply, the pressure to act grows. Geoengineering moves from theoretical discussion toward policy consideration. The idea of blocking sunlight sounds extreme, but so is unchecked warming. Humanity faces a narrowing window. Emission reductions remain essential. Renewable energy expansion is critical, but parallel research into climate intervention continues. In the coming decades, the decision may not be whether we can cool the Earth artificially. The real question may be whether we dare not to, because once the technology exists, the temptation to use it will grow. And when the thermostat of an entire planet is within reach, the stakes could not be higher.